In this video, we will talk about how to determine if a function is homogeneous. So here's the definition. We say that a function f of x comma y is homogeneous of degree alpha if we can write f of tx and ty is equal to t to the power of alpha times f of x comma y. So I have a few examples for us to work through here. Let's check out this first one. We have this function and we want to determine if it is homogeneous. The way that we do that is replace x with t of x and then replace y with t of y and see if we can write the function in this format. So here's what we can write. F of tx comma ty would look like, instead of x squared, we're going to write t of x squared. And then we have plus x times y, so we'll write t of x times t of y. And then lastly we have minus y squared, so instead of y, we're going to write ty. So let's see if we can simplify a little bit. So when we have an expression like this raised to a power, we can raise each individual element to that power. So this would be t squared times x squared. And then we have plus, when we multiply these two expressions together, we can see that we would have two t's, so we would have t squared. So we would have t squared xy minus, lastly we would have t squared y squared. So we'll notice that each of these terms has a t squared in it, so we can actually factor out a t squared. So we can say t squared, when we pull that out, we'd be left with x squared plus xy minus y squared. Now what we'll notice is that this expression in the parentheses is equal to the original function, and we were able to write it as t to the power of 2. So we would say that yes, this function is homogeneous. And we would say that the degree of the function is a 2, since t to the alpha, this alpha right here, turned out to be a 2. All right, let's check out this next example. We want to know if this function is homogeneous. So once again, we'll start by rewriting it as f of tx comma ty. So wherever we see an x, we're going to write tx. So we get tx to the fourth plus, instead of y, we'll have ty to the fourth. And then we just have a minus 4 out here at the end. So if we simplify this, we get t to the fourth, x to the fourth, plus t to the fourth, y to the fourth, and then we just have minus 4. So we'll notice that in this function, each term does not have a t to the fourth, because this 4 right here is just by itself. So we're not able to factor out a t to the fourth. So for this one, we would say, no, it is not homogeneous. All right, let's check out this last example. We have this function, and we want to know if it is homogeneous. So we'll start by rewriting it as f of tx comma ty. So here's what we get. Wherever we see an x, we'll write t of x. So here's what we get. 3 times, instead of x squared, we'll write tx squared, times y. Instead of y, we're going to write ty, and then minus, we'll have ty cubed. So if we expand this out, we'll get 3 times t squared x squared, and then we'll have times ty, so ty, and then minus t cubed y cubed. So we'll notice in this expression right here, we have a t squared and a t, so we can actually rewrite this as 3t to the third times x squared y, and then we still have minus t cubed y cubed. So we'll notice that we can factor out a t cubed from each of these expressions. So we could say t cubed, when we pull that out, we're left with 3x squared y minus y cubed. So we'll notice that this expression inside the parentheses is equal to this original function. So this function is homogeneous because we were able to write t to the power of some alpha. In this case, it turned out to be 3 multiplied by the original function. So for this one, we'll say yes, it is homogeneous and the degree is 3, since that's the degree that we found right here. So those were just a few different examples of how to determine if a function is homogeneous.